In the last lecture, we were discussing binary diffusion. Okay. So far previously, we had used Fick's law for diffusion, where the flux is equal to minus d times the diffusion coefficient. That is the diffusive flux. Convective flux is equal to the fluid velocity times the local concentration fields. And in all of our discussions so far, we had assumed that the fluid velocity is independent of the diffusive flux itself. Okay. However, when there is multi-component diffusion in which different species are diffusing in different directions, there could be a net transport of mass due to these diffusive fluxes. Okay. So, the center of mass could be moving, because even though fluxes may be in different directions, the sum of all the mass fluxes may not be 0, which means that there is the center of mass is moving with a finite velocity. That has to be included in the definition of the flux when we write balance equations, and that is what we were examining in the last lecture. So, you can define two kinds of velocities. One is the mass average velocity and the other is the molar average velocity. Mass average velocity is the sum of the masses of all molecules times the velocity of each divided by total mass. Molar average is the number of molecules. So, it is a number average rather than a mass average. Okay. So, the difference between a mass average and a number average is the difference between a mass average velocity and a molar average velocity. Okay. I had first described for you the mass average description. Okay. Concentration Ca and Cb, density mass per unit volume is mass per unit volume of A plus mass per unit volume of B. Okay. So, that is equal to rho Ca plus Cb. Mass fractions are Ca by rho and Cb by rho. Sum of the two mass fractions is necessarily 1, derivative of that is necessarily 0. The species average velocities in the z direction, say, are Vaz and Vbz. Mass flux is the concentration of A times the species velocity of A. Mass flux of B is concentration of B times the species velocity of B. Total mass flux is the sum of the two mass fluxes. The diffusion coefficient, we had made a slight departure from the previous expression in two respects. One is that we have considered this mass average velocity times the concentration, the diffusion, the flux due to the fluid velocity, the mass average fluid velocity. Okay. And the other thing is we had written, instead of dCA by dZ, we had written this as total mass density times dWA by dZ. Okay. I told you that this comes from thermodynamics. It should strictly be related to the mass fractions rather than the mass concentrations. Similarly for B, and if you sum up those two, you find that the diffusion coefficients DAB, okay, DAB and DBA have to be the same. That is a consistency condition that we had got earlier. Okay. And we had done the exact same thing for the molar average description. Okay. Capital letters for moles, molar average quantities, concentration Ca, Cb, sum of concentrations I have used C, molar fractions, mole fractions Wa and Wb. The expression for the fluxes has the exact same form, except you substitute molar concentrations for mass concentrations and mole fractions for mass fractions. Okay. And this also satisfies the consistency condition dAb equals to dBA. So, in what situations do these additional terms contribute to the total fluxes? Okay. So, that we were considering an example. Dry air above a tube of containing water at the bottom. The tube has height 15 centimeters, the water height is half a centimeter. Water is evaporating, okay, and we want to find out how much time it takes for all of the water to evaporate given these constraints. Okay. So, there are two things here, one is the flux of water and the other is the flux of air. Okay. So, the flux of water vapor, okay, through this tube, okay, the flux of water vapor J W Z. Okay. I will work with mole average quantities for the present. Okay. It turns out in this case mass averages give you the exact same results. J W Z, the expression that we had, minus d water air diffusion coefficient concentration, molar concentration times d of the mole fraction of water by dz plus the mole fraction of water plus the mole fraction of air, sorry, where C is the total concentration. Okay. So, this should strictly be speaking, it should be the mole fraction of air water times the mole fraction, I am sorry, the mole fraction of water times J A Z. Okay. This is equal to rho times V Z, which is the sum of the mole fractions. Okay. So, let me take one step back and write this as, sorry, this is concentration. Okay. Subscript W for water and subscript A for air. Now, we cannot solve this without some relation between JWZ and JAZ, okay, in general, okay, because this contains two equations, and if I write a second equation, I will have once again two variables there. Okay. So, what do you do? One thing is to realize that as water evaporates, right, as water evaporates, the level of water in this, the level of liquid water goes down as water evaporates. Okay. However, the density of, okay, density of water is about 10 power 3 kg per meter cubed. Okay. That is the density of water, and density of vapor. Okay. Water vapor, it will be approximately 1.25 kg per meter cubed. Okay. You know that the density of liquids is about 1,000 times larger than the density of gases. Okay. The density of liquids is about 1,000 times the density of gases. Okay. So, as the water evaporates, the level of the surface goes down. However, the volume of vapor generated is about 1,000 times the volume of the decrease in volume of the water liquid level. The volume of vapor that is generated is about 1,000 times, 800 times to 1,000 times the volume of liquid water. Okay. And the air that comes in to fill the gap that is due to the decrease in the level of liquid water. The decrease in the level of liquid water, that volume, is about 1,000 times less than the volume of the water vapor that is generated. Okay. So, therefore, you can neglect the flux of air coming down in comparison to the flux of water vapor going up, because even though the liquid level is going down and the air has to come in to fill the gap created by the decrease in the level of liquid, that volume is only about 1,000 times less than the volume of water vapor that is going upwards. Okay. So, to within a factor of 1,000, you can 1 in 1,000 you can neglect the flux of air and consider that there is only a diffusion of water upwards. Okay. So, in that case, because the volume decrease in the liquid level is much smaller the decrease in volume of the liquid is much smaller than the volume of water vapor that is generated, you can neglect the decrease and consider the level to be a constant. In that case, there is no air that is coming in, and this term is equal to 0. Okay, so that is the additional constraint that we have over here, okay, for this particular problem. Once we have that, the equation becomes JWZ into 1 minus WW is equal to minus dWA C d or alternatively JWZ will be equal to this divided by 1 minus WW. Okay. You're just taking the last term on the right to the left hand side and then dividing throughout by 1 minus WW. So, I can integrate this once. Okay. The natural logarithm of 1 minus WW is equal to JWZ Z by C d diffusion coefficient plus some constant of integration. Okay. Now, how do we determine the constant of integration? At the surface, the mole fraction of water has to be the saturation mole fraction due to the vapor pressure at that value. Okay. So, at Z is equal to 0, is equal to Ws, the saturation mole fraction, which is equal to the partial pressure divided the vapor pressure divided by the total pressure. Okay. Okay. At the surface itself, the fraction of the number of moles of water is equal to the vapor pressure divided by the total pressure. Okay. So, at Z is equal to 0, it is this, therefore, I get I is equal to natural logarithm of 1 minus Ws. Okay. So, I get logarithm of 1 minus WW by 1 minus Ws is equal to JWZ Z. Okay. This is the equation for the flux. At the top of the glass tube, there is dry air. So, the mole fraction of water has to be equal to 0 at the top. Okay. At the top, the mole fraction of water has to be equal to 0 because there is dry air. At the bottom, the mole fraction will be the saturation mole fraction, which is the vapor pressure divided by the total pressure. Okay. So, I have to use the second condition at the top, where the mole fraction WW is equal to 0 at because it is dry air. Okay. Therefore, I get log of 1 by 1 minus Ws, okay, which is minus log of 1 minus Ws. Note that this is a natural logarithm you get by integrating 1 over WW. Okay. By integrating this term, you get the natural logarithm. Okay. This has to be equal to JWZ H by C dWA. Okay. So, the flux I get will be equal to minus dWA C log of 1 minus Ws by H, and I have to estimate these quantities. Okay. I know what is the diffusion coefficient, it has been given in the problem, okay, 2.2 into 10 power minus 5. Okay. what is the concentration, molar concentration of water. Okay, C has to be equal to P m by kBt. Okay. Sorry, molar concentration, there is no kb, so I will just use P by RT for the molar concentration. P by kBt is number of molecules per unit volume. Okay, so the molar concentration is just P by RT, 1.013 into 10 power 5 okay, newtons per meter square. Okay. This is divided by 8.314 joules per mole per Kelvin into 298 Kelvin, 25 degrees centigrade. Okay. This is 40.9 moles per meter cubed. Okay. And I also need to calculate the saturation mole fraction. The vapor pressure of water is 3.15 kPa. So, this is going to be equal to the vapor pressure by the P atmospheric pressure is equal to 3.15 by should be equal to 3 into 3.1. Sorry, 3.5 kilopascals. Okay, so this 10 power 3. So this note that the vapor pressure is 3.1 kilopascals, which is 3.1 into 10 power 3 pascals, and denominator is atmospheric pressure 1.013 into 10 power 5. Okay. So, substituting these, okay, JW is equal to minus 2.2 into 10 power minus 5 meter square per second, okay, into 40.9 moles per meter cubed into log of 1 minus 0.013 not 31 divided by h, which was 15 centimeters, so 0.15 meters. And if you do the calculation, you will ultimately get 1.89 into 10 power minus 4 moles per meter square per second. Okay. The mass flux is equal to 1.89 okay, into the molecular weight of water. Okay. This turns out to be equal to 3.40 into 10 power minus 6. So, therefore, the mass transfer rate, okay, evaporation rate is equal to mass flux into the surface area. Okay, in kg per second. Okay, the height of water that is evaporated, okay, height of water evaporated okay, is equal to this flux into area, okay, divided by the density, okay, and the density into the area, because the density is 10 power 3 kg per meter cubed, Okay. So, the volume evaporated will be equal to the mass flux divided by area. Okay. So, let us just first take the volume evaporated. Is equal to JWA divided by the density. Okay. This is kg per second divided by kg per meter cubed, okay, which is equal to 3.4 into 10 power minus 6 kg per second divided by 10 power 3 kg per meter cubed. Okay, I should write this multiplied by A. Okay, it's equal to 3.4 into 10 power minus 9, okay, meter into A, meter cubed per second. So, this is the volume evaporated, okay, volume evaporation rate. The decrease in height is the volume evaporation rate divided by the area, okay, decrease in height okay, divided by the area, which is A, okay, and the area cancels out and you just get 3.4 into 10 power minus 9 meter per second. Okay. Okay, so that is the rate of evaporation. Okay. And this works out to 0.29. Okay, if you multiply it by the number of seconds in a day, this will work out to 0.29 millimeters per day. Okay. So, at room temperature, this evaporation rate is actually very small. Okay. So, but this is how you evaluate it. Here, recall that we have taken into account the fact that there is a velocity that is generated. Okay. Because of that, we got the fluxes due to both species. Okay, we got the fluxes due to both species, but we had made an approximation here because the volumetric decrease in the liquid level is much smaller than the volume of gas that is evaporated. Volume of air coming in is much smaller than the volume of water vapor going out. Okay. And because of that, we could neglect the volume fraction, the flux of air, and thereby simplify the problem. So, let me solve another problem for you. There is a reaction diffusion system. Okay. So far we had solved for just evaporation, and there we had used the approximation that the air flux is equal to 0. In this particular case, it is a reaction diffusion system, and the relation between the fluxes will be determined from the reaction stoichiometry. So, I will show you that example. Okay. Okay. Okay, this is a process, okay, where you have an iron slab. Okay. This is iron, okay, and you have carbon monoxide flowing past it. Okay. This thickness is 1 centimeter. Okay. Carbon monoxide reacts here and it produces iron pentacarbonyl, okay, FeCO5. Okay. By the reaction, Fe plus 5CO gives FeCO5. Okay, so, for every 5 molecules of CO that comes downwards, 1 molecule of iron pentacarbonyl will go upwards and into the gas phase. Okay. Reactor height is 1 centimeter, area is equal to 100 centimeter square. and you are given diffusion coefficient d is equal to 2 into 10 power minus 5 meter square per second. Okay. And I will put a coordinate system here. This is z, z equals 0 and z is equal to h. Okay. And the boundary conditions are at z is equal to 0, the weight fraction of CO, okay, the mole fraction of CO is equal to 0, because whatever carbon monoxide comes down gets instantaneously absorbed by the surface, okay, gets instantaneously reacted. So, this is a reaction control process. So, this is a diffusion control process and the reaction happens instantaneously at the surface. Therefore, the mole fraction of iron pentacarbonyl is 0 at z is equal to 0. And at z is equal to h, the mole fraction of FeCO5. This is equal to 0 because the carbon monoxide stream, that flow rate is sufficiently high that the fraction of the stream consisting of iron pentacarbonyl is small. Okay, so, those are the boundary conditions. In this particular case, the fluxes of FeCO5 by of carbon monoxide by FeCO5. This is related by stoichiometry. For every molecule of carbon monoxide that every 5 molecules of carbon monoxide that comes down at steady state, 1 molecule of iron pentacarbonyl goes up. Okay. Flux of carbon monoxide is downwards, flux of iron pentacarbonyl is upwards, opposite directions, and the ratio of molecules is 5:1. So, this ratio is equal to -5. So, this is the constraint between the two fluxes. Okay. Now, if you write the diffusion equation for the mole fraction of iron pentacarbonyl, okay, you get JFeCO5 is equal to minus dCdW FeCO5 by dZ plus W FeCO5 into JCO plus JFeCO5. Okay. The average velocity is the molar average velocity is the molar fluxes times the concentration, and I have written the concentration of FeCO5 as the mole fraction times the total concentration. Okay. So, this is the equation, but we have this relationship here. We have this relationship, and therefore, we can get a relation between JFeCO5 and JCO. Okay. And if you use this equation simplifies to JFeCO5 is equal to minus D minus 4 W FeCO5 J FeCO5, okay, using this relation because JCO is minus 5 times. Okay. Take it to the left side and you will get and once again divide throughout, okay, by 1 plus 4 FeCO5. So, I will get J Fe FeCO5 is equal to minus dCdW by dZ. Now, and you can integrate this, okay. You will get, okay, take dz to the left side and then integrate, because the flux has to be a constant at steady state. J Fe CO5 Z by dC is equal to minus ln of 1 plus 4 W Fe CO5 by 4 plus a constant of integration. This is determined from the condition that the weight fraction of FeCO5 is 1 at the bottom surface. At Z is equal to 0, weight fraction of CO is equal to 0. I said that CO gets consumed instantaneously, which means that W of FeCO5 is equal to 1. Okay. And if it is equal to 1 at Z is equal to 0, this gives me the value of I is equal to log of 5 by 4. Okay. Also at Z is equal to H, right, W Fe CO5 is equal to 0. I said the weight fraction can be approximated as 0 because at the top surface the stream is sufficiently fast that there is very little concentration of FeCO5 there. And substituting that and Z is equal to H, you will find that J FeCO5 is equal to dC by H log of 5 by 4, natural logarithm. Okay. So, this gives us the expression for the flux. Okay. Now, we only have to substitute. Okay. The concentration is equal to P by RT. We are given that this reaction takes place at 150 degrees centigrade. Okay. T is equal to 150 degrees centigrade, which is equal to 423 Kelvin. Okay. So, this is equal to 1.013 to 10 power 5 Pascal divided by 8.314 joules per mole per Kelvin into 423 Kelvin, which is 28.8 moles per meter cubed. Okay. So, therefore, JAZ is equal to D is 2 into 10 power minus 5 meter square per second into C is 28.8 moles per meter cubed by H is 0.01 meter, 1 centimeter times natural logarithm of 5 by 4. Okay. This is equal to 2.3 into 10 power minus 2 moles per meter square. And I can multiply this now by the molecular weight. Okay. The molecular weight of FeCO5 is equal to 195 grams per mole, which is 0.195 kg per mole. You can get this from the molecular weights of carbon, oxygen and iron. Okay. Therefore, the mass flux, okay, of FeCO5 is equal to 4.54 into 10 power minus 3 kg per meter square per second. Okay. And you can multiply this by the cross sectional area to get the mass production rate. okay, by the cross sectional area in kg per second. Okay. So, the cross sectional area is 100 centimeters square, which is 0.01 meters square. So, you have to multiply this by 0.01 and you will get 4.54 into 10 power minus 5 kg per second. Okay. So, that is how we calculate the flux in this case. In this case, there was a reaction. Okay. So, the relation between the two fluxes, the molar fluxes of the two species was constrained by reaction stoichiometry. Okay. And that we used in order to get a relation between the two, and therefore, this total flow rate was obtained by the relation between the two fluxes. Okay. So, this completes our discussion on binary diffusion. I will briefly review this in the next lecture before we proceed to looking at use of correlations in time varying and spatially varying problems. I will continue this in the next lecture. I will see you then.